5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. So when we reach 0 factorial, the obvious guess seems unavoidable. There is a 0, so the answer should be 0. But every calculator, textbook, and branch of combinatorics says 0 factorial equals 1. Is that merely a convenient definition, or is 1 the only value that keeps the structure of mathematics intact? We will run factorial backward, count arrangements of nothing, multiply an empty list, walk the edge of Pascal's triangle, and finally extend factorial into a smooth curve. Every path lands on the same apparently impossible answer. This is symmetry. Let's find out why. First, forget 0 and watch how neighboring factorials are connected. A factorial multiplies every positive whole number from its input down to 1. 5 factorial is 120. 4 factorial is 24. 3 factorial is 6. 2 factorial is 2, and 1 factorial is 1. Notice the ratio between neighbors. 5 factorial divided by 5 gives 4 factorial. 4 factorial divided by 4 gives 3 factorial. Each downward step removes the first factor. This relationship is more fundamental than the written dots in a product. N factorial equals n times n minus 1 factorial. It lets the sequence grow upward, and when division is legal, lets us walk backward as well. For example, 6 factorial is 6 times 5 factorial, so 6 times 120 gives 720. Now take the final legal step. 1 factorial equals 1 times 0 factorial. The left side is 1. Multiplying by 1 changes nothing, so the right side is simply 0 factorial. Therefore, 0 factorial must equal 1. The same conclusion appears if we continue the ratio pattern. 2 divided by 2 gives 1, and 1 divided by 1 gives 1 again. Nothing is being divided by 0. We are dividing 1 factorial by 1. Defining 0 factorial as 0 would break the neighboring identity at its very first boundary, because 1 times 0 would incorrectly make 1 factorial equal 0. The pattern reaches 0 without ever using 0 as a multiplying factor. This is not circular reasoning. We already know what factorial does for positive integers, and we want the same recurrence to remain true at 0. There is exactly one value that works. If 0 factorial were 2, then 1 factorial would become 2. If it were 0, every higher factorial generated from it would also collapse to 0. Choosing 1 preserves both the known sequence and its multiplication rule. Mathematicians often extend a definition to a boundary this way. Identify the structure that must survive, then ask which boundary value makes all adjacent cases agree. Here, the extension is unique. It preserves old results while adding one new input with no special repair rule. The algebra says 1. Counting explains what that 1 actually represents. Factorials count arrangements. With 3 distinct cards, choose the first position in 3 ways, the second in 2 ways, and the last in 1 way. 3 times 2 times, 1 gives 6 possible orders. With 2 cards, there are 2 orders. With 1 card, there is 1 order. This multiplication is the rule of choices. If one decision has 3 options and the next has 2, there are 6 complete paths through the decision tree. Factorial is therefore not merely a compact product. It counts how many complete ordered outcomes exist. Every leaf of the tree is one finished arrangement, so counting leaves gives the factorial value. Now remove every card. How many ways can 0 objects be arranged? It is tempting to say 0 because there are no visible arrangements to draw. But the question asks for complete outcomes, and there is one, the empty arrangement. You do nothing, place nothing, and the task is complete. There are not 2 different ways to do nothing, and there are not 0 valid outcomes. There is exactly 1 empty sequence. Computer science writes it as an empty list. Combinatorics calls it the empty permutation. 0 factorial counts that single valid object. Its length is 0, but the sequence itself exists and satisfies every requirement. The distinction is between having no objects and having no outcomes. A locked door with no valid code has 0 outcomes. An instruction that says, arrange all objects from an empty box has 1 outcome, because the empty sequence satisfies the instruction. This matters whenever larger constructions contain an empty case. If we counted that case as 0, multiplying by its count would erase every larger object built around it. Counting it as 1 says, the empty component contributes no choices, but does not destroy the construction. 1 is the neutral count for a completed choice with nothing left to choose. The same idea appears inside multiplication itself. Suppose a running product begins at 1. Multiply by 3 and it becomes 3. Multiply by 4 and it becomes 12. Multiply by 5 and it becomes 60. Before the first factor arrives, what value should the product have? It must be 1, because 1 is the multiplicative identity. Multiplying by it leaves the first real factor unchanged. Starting at 0 would make every product 0 forever. In algorithms, this is exactly how a product accumulator works. Initialize it to 1, then multiply in each item. If the list contains no items, the loop performs no updates and returns 1. This makes empty and non-empty inputs obey the same program without a separate exception. This is called the empty product. The product of no numbers is 1, just as the sum of no numbers is 0. The two rules use different identity elements. 0 is neutral for addition because a plus 0 equals a. 1 is neutral for multiplication because a times 1 equals a. 0 factorial is the product of every positive integer less than or equal to 0. That collection is empty, so its product is the multiplicative identity, 1. The rule is not a trick unique to factorials. It is the general convention that makes products behave consistently across empty sets. It also lets products split and recombine even when one portion contains no factors. Empty products appear naturally when formulas split objects into independent parts. Imagine multiplying the sizes of several choice sets. A part with one option contributes a factor of 1 and leaves the total unchanged. A construction with no parts at all also has one empty assembly. This mirrors the empty arrangement exactly. The algebraic identity and the counting interpretation are not separate coincidences. They describe the same neutral object from two directions. Multiplication says no factors change 1. Combinatorics says no choices produce one empty completion. 0 factorial cites where those two structures meet. A third proof is hiding along the edge of the most famous counting triangle. Factorials also count combinations. The number of ways to choose k objects from n is n factorial divided by k, factorial times n minus k factorial. Take 5 objects and choose 2. The formula gives 5 factorial over 2 factorial times 3 factorial, which is 10. A visual grid of pairs confirms the answer. The denominator removes the internal order of the chosen group and the unchosen group, because choosing A then B is the same pair as choosing B then A. Factorials make the symmetry between chosen and unchosen objects exact. Choosing 2 and leaving 3 is therefore counted consistently from either side of the split. Now choose 0 objects from 5. There is exactly one possible selection. Choose none of them. So 5 choose 0 must equal 1. Put 0 into the formula. 5 choose 0 equals 5 factorial divided by 0. Factorial times 5 factorial. The 5 factorials cancel, leaving 1 over 0 factorial. For the answer to equal 1, 0 factorial must equal 1. If it was 0, the formula would divide by 0, and the entire left edge of Pascal's triangle would disappear. A single boundary value protects every row. The opposite edge, choosing all 5 objects, gives the same calculation and the same requirement. Pascal's triangle makes the boundary visible. Each interior number is the sum of the two numbers above it. Every row begins and ends with 1 because there is one way to choose nothing and one way to choose everything. Those edge ones are the anchors that let the addition rule generate the interior. The factorial formula reproduces the same triangle only when 0 factorial equals 1. So recursion, direct counting, and Pascal's addition rule all agree at the boundary. Change 0 factorial and these independently useful descriptions stop matching one another. The same boundary value survives when factorial leaves counting and enters calculus. The exponential function can be built from an infinite power series. It begins 1 plus x squared over 2 factorial plus x cubed over 3 factorial and continues. Written uniformly, the term with index n is x to the n divided by n factorial. The first term uses n equals 0. It becomes x to the 0 over 0 factorial. For non-zero x to the 0 is 1, and 0 factorial equal to 1 makes the constant term 1. That is exactly the value the exponential function needs at x equals 0. The boundary convention lets one formula include every term without a special exception. It also aligns the derivatives, because differentiating shifts each factorial coefficient neatly into the previous one. Factorial can even be extended between the whole numbers. The gamma function draws a smooth curve through the factorial values, shifted by 1. Gamma of n plus 1 equals n factorial. At n equals 0, this says gamma of 1 equals 0 factorial. Gamma of 1 is the area under e to the negative t from 0 to infinity. That area equals 1 exactly. So the continuous extension lands on the same boundary value. The curve was not designed merely to rescue 0 factorial. Its integral and recurrence independently reproduce the entire factorial staircase. Halfway between integers, it supplies new values while still meeting every familiar factorial point exactly. This convergence of explanations is why mathematicians treat 0 factorial equal to 1 as natural rather than arbitrary. The backward recurrence demands it. The empty arrangement counts it. The empty product identifies it. Combination formulas and Pascal's triangle preserve it. Infinite series and the gamma function extend it. Any one argument is enough to define the boundary, but together they show that one value connects many parts of mathematics with no patches. Good definitions compress structure. They make different theorems become instances of the same rule. When unrelated calculations agree on a boundary value, that agreement is powerful evidence that the definition has captured something real. If factorial reaches 0 so cleanly, why not continue to -1? Try the same recurrence one more time. 0 factorial should equal 0 times -1 factorial. But 0 factorial is 1, so the equation becomes 1 equals 0 times -1 factorial. No ordinary number can satisfy it. Equivalently, walking backward would require dividing 0 factorial by 0, which is forbidden. The first genuine break is not at 0 factorial, it is at -1 factorial. 0 is the final point where the recurrence can be extended without division by 0 or contradiction. This boundary is therefore discovered by the same rule that made 0 factorial possible. The gamma curve shows the same obstruction geometrically. It passes smoothly through 0 factorial, 1 factorial, 2 factorial, and every positive factorial. But at -1, -2, and the other negative integers, the curve shoots without bound on both sides. These vertical barriers are called poles. Between them, gamma still assigns values to many negative non-integers, such as -1/2, but it cannot give finite values to the negative whole numbers. The discrete recurrence and the continuous curve fail at exactly the same locations. So the exclamation mark after 0 does not mean multiply by 0. It asks for the factorial of 0, the product of an empty list, and the number of arrangements of an empty set. Both equal 1. That value is forced by the recurrence, protects the edges of Pascal's triangle, supplies the first term of the exponential series, and sits naturally on the gamma curve. The surprising equation is not an exception taped onto mathematics. It is the last perfectly consistent step before the true boundary at -1. One empty product, one empty arrangement, 5 proofs, 1 answer. If this changed how 0 looks to you, subscribe to Symmetry for the next visual deep dive.